Good morning, students. I welcome you all for another lecture on the course Computer Architecture and Organization. In today's class, I am going to discuss about the logical instructions in ARM processor. In the last few classes, we discussed about the features of ARM processor, and thereafter we discussed about the indexed addressing modes which frequently used in ARM processor. And in the next, we discussed about the different arithmetic operations in ARM processor. In today's class, I am going to discuss about different logical instructions which are used in ARM processor. We know that the logical instructions are used to perform the logical operations like logical AND, logical OR, logical XOR. So in order to perform all these logical operations, we have a dedicated instructions are present in ARM instruction set. In this class, we are going to discuss all those logical instructions along with shift and rotate related instructions. Right. So before discussing about our different logical instructions which are present in ARM processor, the first thing you have to know about what are the logical instructions we have in ARM processor to perform logical operations. In that case, to do a logical AND, logical OR, logical XOR, as well as bit clear for these particular operations, we have a dedicated instructions present in the instruction set of ARM processor. To do this logical AND, we have an instruction is AND. To do logical OR, we have an instruction is ORR. To do exclusive OR, we have an instruction is EOR. To do a bit clear, we have an instruction is BIC. These are the different mnemonics to do this logical operations in ARM processor. Next, coming to the instruction format, how it looks like for these logical instructions. If you are thinking that direction, what is the instruction format we use for arithmetic instructions of ARM processor? The same instruction format here we are using for logical instructions. See here, guys, this entire instruction have a different fields. The first field always represents about operation code, which indicates which operation we are going to perform by using instruction. And the operand which follows operation code we consider as a destination operand. And next two operands we consider as a source operand. Source operand 1 and then the source operand 2. This format is same as our arithmetic instructions. So now we will go and discuss different logical instructions one by one in the sequence. The first instruction was AND R1 comma R2 comma R4. So in this AND represents operation code. This AND indicates do logical AND between the source operands. Here our source operands are CPU register R2 and CPU register R4. Do logical bitwise AND between the contents of these two registers. At the end, the result can be copied into another CPU register R0. The meaning of this one is R2 content is a logical AND with R4 content. Result was a transfer to R0. We know that in ARM, each and every register size is equal to 32-bit because our processor is 32-bit itself. If I took an example for this, the content of register R2 is 0, 0, 0, 0, 0, 0, 3, 8, H. This is a 32-bit number. And similarly, I assume the content of register R4 is like this. It is F, 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 0, 0, H. Then do logical AND bitwise between the contents of R2 and R4, the final result goes to R counter. So here this is equivalent to, if you go and write the binary equivalent for this, so these equivalent to 16 zeros, and this is equivalent to another 8 zeros. That means a higher order 24 bits are zeros, and lower order only 2 digits, that is a 3 and 8, have their own hexadecimal equivalent in binary form, right? So for this, these are 24 are zeros. This is like this, and coming to 3 is equal to 00, 11, and followed by 8, that is 1 followed by 000, that is the binary equivalent of first number. And coming to for R4, its content is 6F00H, that means this is equivalent to total 24 ones followed by 8 zeros, because we know that F is equivalent to 4 ones in binary. So this is equal to, and so on, 4 ones. So this is up to 24 bits, and followed by 00. 0 is equivalent to 4 zeros, another 0 equal to 4 zeros. Now do bitwise logical AND between these are two numbers. Just you remember, friends, logical AND operations, if the inputs both are 1 and 1, then only output is 1. For remaining cases, the output is equal to a 0. So in that process, up to this, everything we are getting a zeros, because here one of the input is equal to 0, and next 2 zeros, again 0, 0. So here also again all these things is equal to 0, 0. Because we know that for an AND gate, both inputs are 1 and 1, then and only output is equal to 1. For remaining cases, it is equal to 0. If you are observing the inputs of both the R2 and R4 values, nowhere we didn't found both the inputs are 1 and 1. If one input is 1, other input is obviously 0. Because of that, the resultant is equal to 0. So here the final value is equal to 8 zeros H. This is our result after logical AND between these R2 content and R4 content. This is the final value was copied onto another CPU register R. So here you remember, friends, this bitwise logical AND was done between R2 and R4 in parallel. That means the logical AND was done between R2 and R4 all bits in parallel. Simultaneously, we are doing a bitwise logical AND between the content of R2 and R4, and final result was a transfer to another CPU register, which is R. So this is how a logical AND operation is going on in ARM processor. Fine. Coming to the second, that is the instruction which is used to perform logical OR. This logical OR operation we can also call as inclusive OR. You remember that, guys. As logical OR is also called as inclusive OR. So the meaning of this one is do logical OR operation between the CPU register contents R4 with R2. At the end, the result was a transfer to another CPU register R2. So here the meaning of this is the content of CPU register R2 is ORing with another CPU register content R4. The final result was a transfer to another CPU register R2. So again here also these register sizes are 32-bit. We know this because our processor is 32-bit processor. And this R0 size also 32-bit. So how we are doing a previous occasion logical AND between these two register value in a similar operation by using this instruction we did the logical OR operation between these two register contents in parallel. At the end the result was a transfer to OR. Just you remember, friends, again STLD, that is how the logical operation is going on. For an OR gate, if both the inputs are 0, then only output is 0. If both inputs of OR gate is equal to 0, output is equal to 0. For remaining cases, the output is equal to 1. That means the both inputs are 1, 1, or one input is 0 and another input is 1. For these cases, the output of OR gate is equal to 1. You remember that based on that logic, internally this instruction was executed in ARM processor. I tell you one more time, that is, we did logical OR operation between the content of register R2 with R4. The final result what we are getting, that is simply transferred to another register R0 in ARM processor. So this is about the logical OR related instruction. Next, the third instruction is EOR. You remember friends, this is for exclusive OR. Previous case I tell you that ORR represents inclusive OR, and here EOR represents exclusive OR. So this exclusive OR we can also call as modulo 2 addition. This exclusive OR we can also call as modulo 2 addition. That means if you do exclusive OR between two numbers, if both are different, output is equal to 1. If both inputs are same, output is equal to 0. So that operation was done with the help of this particular instruction EOR. Here our example is EOR space R0 comma R6 comma R5. That means do logical XOR between the content of CPU register R6 with R5. The final result was a transfer to another register R0. How I did in case of AND instruction in a similar way, here also we did an example for this instruction. We know that R6, R5 and R0 all are 32-bit numbers. Here again I assume the content of R6 is like this. So 6 zeros, 1 3H, and coming to R5 value, it is 6 zeros, 7 8H. So I am not bothering about this because these 6-digit values are 0. If I did a logical exclusive OR between these 6 digits, obviously my result is equal to 0 because here the inputs are same, output is equal to 0. I would like to focusing on last 2 digits. Here it is 1 3, equivalent binary value is 1. This 1 3 is equal to 0001 and 1 000. Sorry, it is this. Sorry. So 1 3 is equal to 0001 and 0011, and 7 8 is equal to 0111 and 1000. Now do logical XOR between these two. So inputs are different, output is 1 if the inputs are same, output is equal to 0. Here the final value is equal to this is 6 and this was a B. So final result what we are transferred to the destination register R0 is 6 zeros followed by 6DH. This is the final value. We can copy it on to the destination register R0. So here also this logical exclusive OR operation is done in parallel between the contents of R5 and R6. Fine. Go for one more example. So one more instruction, that is BIC R0 comma R3 comma R4. The first thing you have to remember, friends, about this instruction is here this BI represents bit and this C represents clear. So simply BIC means bit clear. It is one type of AND related instruction. AND related instruction. Why? Because internal operation is related to logical. So here the operation is, you remember friends, first go and take a complement for the content of register R4. That means first you take inversion of the content of R4. I simply here written as R4 bar. That means complement of R4. After complementing the content of R4, then the result was a logical AND with the content of another CPU register R3, and the final result was a transfer to another CPU register R4. So what is the difference between normal logical AND and here bit clear is, before doing a logical AND in this case, first we can go and take a complement for the second operand. Here my second operand is R4, First I took the complement for the content of R4. After taking a complement of it, the resultant was a logical AND with the second operand R3 value, and final result was a transfer to a CPU register or not. So that is the difference. But in case of a logical AND, we didn't do this type of a complement before doing a logical AND. But in case of DIC instruction, first we took the complement for the second operand, that is your R4. After complementing the content of R4, then we do logical AND with the second operand, that is R3 value. Final result was transferred to R. So it is the mixing of two operations. One is complement. One operation is complement, and the second operation is logical AND. The second operation is logical AND. It is a combination of these two, DIC. So finally, DIC is a combination of a complement and logical AND. Next, the next instruction is MVN. So again, this MVN represents your MB represents move, your MB represents move, and this N represents not. N represents not. Now listen friends carefully. This MVN is a combination of two operations. First one is a logical operation. The first one is a logical operation. It is not or a complement. And the second operation is data transfer. Second operation is data transfer, which is nothing but move. This MVN is a combination of these two instructions. So see here friends, our example is MVN space R0, Rn. That means first to take a complement of the content of R1. That means take inversion of the content of R1. Later that result is a transfer to another CPU register R0. So here I am not straight away transferring the content of R1 to R0. First I took a complement to the content of R1. Later that result is a transfer to a CPU register R0. These are the sum of logical instructions which are used to perform logical operations in ARM process. In addition to this, we have some more instructions comes under this logical group. Those are used to perform somewhat different operations like a shift and a rotate operations. One important thing regarding to this shift and a rotate operations is generally this shift and rotation operations involved in different arithmetic or logical instructions right away. That means we are not using as a separate instruction like a previous case. You may use these instructions separately, as well as we may go and incorporate these logical operations internal to some other arithmetic operation as well as some logical operation. I'll go and give more information about this. So here my instruction is ASR, means arithmetic shift right. You can use this as a separate instruction, or you may go and use this is a part of our instruction. For example, here my instruction is like this: add R0, R1, R2, ASR hash 2 times. Here my instruction is like this. ASR is a part of this instruction. We know that ASR means arithmetic shift right. ASR means arithmetic shift right. Based on the past information, we know that arithmetic shifts are basically used to preserve a sign of a number. It is only possible in arithmetic shift right, but it is not possible in arithmetic shift left. That's why arithmetic shift left is called as a logical shift left also. So here the meaning of this particular instruction is, before doing addition between the content of R1 with R2, first you have to go and apply arithmetic shift right on the content of register R2 by 2 times. I repeat the meaning of this. Before doing addition between R1 content with R2, first you have to go and do arithmetic shift right on the content of R2 by 2 times. Later the result was adding with R1, and final result was stored in register R1. Once again, I'll tell you guys, you remember, you may go and use this is as a separate instruction, or it may incorporate in some of arithmetic or logical instruction. There are two possibilities, the usage of this particular shift and rotate instructions in ARM class. And similarly, the next one is LSR. That means L represents logical, S represents shift, and R represents right. Logical shift right. So this case also similar to ASR. You may go and use this is as a separate instruction to do logical shift right on any specific register, or you may go and use this logical shift right as a part of some arithmetic or logical instruction. So again, I took an example, SUB, that indicates subtract, R0 comma, R1 comma, R2 comma, LSR comma, hash, sub5. The meaning of this instruction is, before subtract R2 value from R1, you know that, just you remember arithmetic instruction what I discussed in the last class. In case of a subtraction operation, the last operand can be treated as subtrahend and this can be treated as a minute. So that's why here what I am saying is, before subtracting the content of R2 from R1, first of all you have to do logical shift right the content of R2 by 5 times. First what we have to do is, we just apply logical shift right operation on the content of R2 by 5 times. Later the produced result was a subtracting from the content of R1, and final result was a transfer to another register R1. So here again, I tell you guys to remember, you may go and use this LSR as a separate instruction, or you can go and use it as a part of some arithmetic or logical instruction. So why we are doing this shifts or rotates? We know that in order to increase the value or in order to decrease the value, then you can go and use this shift operations. We remember that. And coming to the next, LSL. LSL means logical shift left. Previously LSR is logical shift right, and here this L represents logical, S represents shift, and again L represents left. Again this also we can use as a separate instruction, or we may use this is a part of another arithmetic or logical instruction. I'll give an example for this also. Some add R1 comma, R2 comma, R3 comma, LSL comma, hash 3. The meaning of this one is, before adding R3 content with R2, first apply logical left shift on the content of R3 in order to increase whatever the value already R3 has. We know that by doing of logical left shift, the input data is multiplied by 2, we know that. So here I can go and shift left the content of R3 by 3 times, means indirectly we are doing R3 content is multiplied with 8. Because one time we are shifting to the left side by 1 bit position, the resultant is input data is multiplied with 2. If you are doing 2 bits left shifting, the resultant is input data is multiplied with 4. If you are doing a 3 times left shifting, the resultant is input data is multiplied with 8. So here what I am saying is R3 content left shift by 3 bit positions. That means indirectly we multiplied R3 value with the 8. That means I increased whatever the value R3 has initially. Thereafter, this R3 value is added to R2, and final result was stored in a register R2. So here also the scenario was seen. You can go and use LSL as a separate instruction, or you may go and use this is a part of any arithmetic or a logical operation. That you remember. And here ROR, that means rotate right without carry. Rotate right without carry. So again this is also, you may use a part of an instruction, or you can go and use this is also a separate instruction like a previous case. Again I took an example here. Add some R1 comma, R2 comma, R3 comma, ROR comma, hash some 4. The meaning of this one is, before doing addition between R2 content with R3, first you can go and apply rotate right on the content of R3 by 4 times. By doing of this, what happens is, here we are doing a 4 times rotate right. That means whatever the least significant needle I have in R3, that was shifted to most significant side. Because we know that rotate right, the bits are moving from MSB end to the LSB end, and whatever the bit I have in LSB, that is again moved to MSB position. By doing a 4 times rotate right, what happens is whatever the least significant nibble I have before execution of this rotate right operation in a R3, that nibble was now moved to the most significant. And thereafter, just that R3 value is adding with R2 value, and final result was a transfer to R1. So here you remember, friends, in ARM processes, to do logical operations, we have a logical instructions right away. At the same time, we have a logical shift operations or rotate operations as well as arithmetic operations. The related instructions are there. We can go and utilize them as a separate instructions, or maximum occasions we use this shift and rotate operations a part of arithmetic instructions. I hope you understand what are the different logical instructions ARM processors support. So thank you for patient listening. We'll meet in next class.